Okay, so let's continue with neural style transfer, and the picture that was here, I wrote it here. Here we need to calculate the cost between content and generated, and this is the content cost, and then we have a style cost between the style and the generated image. And this here is the formula. And we have two parameters, hyperparameters, alpha and beta. So these are hyperparameters, yeah? And they allow us to weigh the importance of content and or style. Now, how do we calculate the content cost here? Well, we know that it's a feature activation of one of the deeper layers. And in our case, we chose to tap the signal from block 4, layer 3. Yeah? So it's a ReLU from block 4, layer 3. And the content cost is nothing more than the mean squared error. So we're measuring distances here. So it's half of, and then the sum over I and j of the activation of layer L times the content image ij minus the activation of layer L, the generated image ij. And this we're gonna square. Alright, so that's mean squared error. Not very difficult to understand. Now for the style cost, things are a bit more complicated. Yeah, because we want to use all layers. We want to tap from the features of all layers. And you could think, well, the deeper layers are more abstract, so they probably don't add much value, but they do. We also have to consider the deep layers, and this will result in smoother transitions, in better images. Now, in order to calculate the style cost, I need to introduce a new concept that we call the gram matrix. And we'll abbreviate it by GM. So what is the gram matrix? And we will use an example from VGG60. So assume that we're going to use the second block of CovNets, the last layer. So this one here. Yeah, so the feature maps are 112 by 112. So this is our S image here, and this is our G image. All right. So then the size, and these are your filters. You have a depth amount of filters, and a depth amount of filters in our case is 128. Yeah, so you have 128 filters. All right, and the layer that we will use has 112 by 112. So 112 by 112. All right, and anything else? No, just that we're gonna use filter number 1. Now this is filter number 1. And this will be our gram matrix here. Gram matrix. Alright, so we have the sizes, we have everything. Now, all these three images have to have the same size. So if they're not, we need to pre-process a little bit. And basically what we're going to do is we're going to calculate the gram matrix here, the gram matrix there, and then compare them. How do I calculate the gram matrices? Well, in this case, I would call this XS, yeah, this matrix here, and I'm going to multiply that with its transpose. And here I'm going to do exactly the same. XG times XG transpose. All right, that's how we will calculate the values. And then we will compare. We compare pixel by pixel. So first I'm going to compare this one with this one. Alright? Then I'm going to compare this one with this one. Alright? And that I do for all 128 filters. So for the filter number 1, this is the value you're going to get here. Alright? So we have the size of the gram matrix is the size of the number of channels. So it's 128 by 128. And what is this? This matrix is basically gives a number that is reference for the similarity of these filters. Because if we want the style to be the same, we want to use several or similar filters, because these filters are going to trigger features. So here, this is not the gram matrix, this is the delta. These are the gram matrices, and this matrix is actually comparing these two. Calculate the distance between these features, right? So the formula for style cost, basically what we're gonna do is we will sum over all layers, but because here we look at all layers, and then we have a weight WL, and the weight can basically change how big the impact is of one layer compared to another. Yeah. And then we're gonna open the brackets and have 1 divided by 4 times n square m square for layer L. And n is here. N is, sorry, capital N is the number of filters. In our case is 128. Right? And then m square, m is the size of the activation maps. So these are these two. So m in our case is 112. Alright, and then we have the other sum over I and j, where we basically take the gram matrix in a layer L times Sij, which is the gram matrix of the style, yeah, and you subtract the gram matrix again with the same layer L with the generated image, and here again so here again you take the square, yeah, and this is this matrix. Delta means the difference between these two gram matrices, and basically it's a measure of similarity. Yeah. Alright, so we will not do a coding session on this one.